Mhm. So far we learn about the origin of the magnetism in from the classical view and the quantum mechanical view, and also I introduced about the band structure to understand the behavior of the ferromagnetic materials. So from today, I'm gonna move on to the next chapter, and we're gonna talking about the what kind of energy will determine the behavior of the ferromagnetic materials. So first, I would like to introduce the meaning of the energy and force and some related dynamics in this sense. Okay. So not only the magnetism system, but including any kind of the physical system, we need to determine the energy of the system to understand what's going on in the given system. For example, if you have a system energy, and if you take the gradient, and with the minus sign, we get a force caused by this energy term. In other sense, instead of the gradient, sometimes you represent this kind of derivation notation. And one of the simple example is the Newton's second law. The m multiply the second derivative of the position is minus the energy, it's gradient of the energy. And in this equation, what we can learn is if the energy derivation is zero, means it implies the force is zero. So zero force means there's no more external force, so there's no acceleration. So they're gonna keep the velocity of the this object. So in other words, in a stable point, there's two requirements. The first one is the force must be zero. And also the second derivative of the energy must be zero, means it's stable. If this is not, if they have a negative one, that means if we draw the energy in terms of the position, function of the position and energy, this is means the stable point, and this kind of one is also generate the zero derivative, but this point what we call the unstable point, right? So around the stable point, that is very important because in our university, I'm sorry, in our universe, um, everything is around the stable point. Yeah, there is some kind of exceptions. There is some very dynamic situation. There's far from the stable point, but most of the situation is around the stable point. For example, okay, so let's think about this ball pen, and they consist by many molecules, and each molecule are very stable, right? So means they working around this kind of energy stable point. So in many physics, we don't care about this kind of high excited state is not necessary to consider. So according to this idea, any kind of energy can be expressed by this Taylor series in terms of the variable x. And we already know we are talking about the stable point. This first derivative is always going to zero. It's not necessary. And this is a constant term. So only important physics governed by this kind of shape of energy. And as you see here, this term, if we ignore the stable point, and if we move this ground state to the left-hand side, the energy term always expressed by this kind of quadratic form of the variable x. And here the k is the kind of constant which depends on the second derivative of energy. So in a ground state, energy, the first derivative of energy is always zero, and the second derivative is we can assume a constant value, which one is related to the. If we assume this energy term is the harmonic oscillator, the physical meaning of K is the spring constant, right? So the second derivative of the potential energy of the system is working as a spring constant. So what's the physical meaning of the spring constant? If you have some spring, and the spring constant means if you give a given force, and the elongation of the distance is, let's say, L. This is definition of the spring constant. So small spring constant means if you give some given f, the variation of L is, in other words, this one. So if we have a small spring constant for the given force, the elongation is large, so its variation is large. Or the response to the external force is very sensitive. In opposite case, if you have a very large K, then even though we give some given force, the elongation of the spring is very small, right? So it's more stiff to the external force. So the meaning of the second derivative of energy is that the frequency of the oscillation is okay. Then the natural frequency of this given system is written by square root k over m. And this is also depends on the second derivative. So many kind of physical phenomena is related to the vibration of the system. And in the case, the frequency is very important. And this omega is actually very important characteristic of the given system. And they are governed by the mass of the system and the spring constant of the system. So it implies if we have a large K, means it's difficult to change the system by the given force, then we have a large omega. Just imagine that if you back to the classical physics, the large K implies if you have some string in a given length. Okay. And if you give a high tension to the string, for example, in a violin or guitar, you can adjust the tension of the string by changing the rotating knob. Okay, then you got a higher frequency if it is more tensions, right? And if you lose, the frequency will be lower. It's quite a similar thing. And also, if you have a heavy thick wire, usually the sound, if it is large, then the sound, the frequency is lower. Means if your thick string, the natural frequency is lower. It's well matched with your experience. Like if you are not the guitar player, but you know the thicker wire generates the lower frequency sound, right? It's quite a similar thing happens in a solid state. Okay, so please remember this idea. And this idea we can apply in many kind of dynamics, especially in our case, related to spin dynamics. So if you measure the frequency of your system, for example, the spin frequencies, then we can estimate this value, or you can estimate the energy of your given system. Okay, and also this is related to the electron motion in a conduction band. So that's why we learn many times about the simple harmonic oscillator, because they are very important, and we can easily model many physical situations to this simple harmonic oscillator. So that's why I recall this one. Okay, so I just emphasize the energy is important to understand the physics for the given system. So what kind of energy will be involved in a magnetism? So from now on, I'm going to introduce several energies, and each energy is very important, and they will determine the dynamics of the spins or magnetization. Okay, the first one is magnetostatic energy. Actually, that is very important, but I think many students have some problem to understand the magnetostatic energy meaning. And also the magnetic energy, there are several different names called the demagnetization energy or shear balance of energy. And there are many kind of representation, but basically they are same origin. They have a same origin. So what is the origin? Okay, so let's assume I hope you all learn about if you have a magnetic field in a space, we have a magnetostatic energy defined by this equation. This means this is the energy density, and this is the volume integral. So this one means if you have a field of the H in a space, then the energy with this field in the space is larger than the vacuum energy, certain amount of this magnitude. It's similar, the electric field, we have a such energy density, for the electric field. So means if we have an electric field or the magnetic field, it's the energy of this space is higher than vacuum. Okay? So if we take in the integral, volume integral, we got the total energy. This is the definition of the demagnetization energy. So yeah, I hope all students remember this result from the electromagnetism course. So the magnetic energy means this kind of energy, and what we need is we need to minimize this magnetostatic energy to stabilize the system. Okay? Okay. Okay. So how we can minimize? Oh, okay. So look at this equation. The H is integrand is square, so it's always positive. They are always positive. So reduce this total demand energy. What you can do is we have to reduce the magnitude of the H, or we need to minimize the volume where the magnetic field exists. Okay. So as a consequence of this energy minimization of the magnetostatic energy, the magnetic moment will be aligned to minimize this energy. So that's what we call the shape anisotropy. For example, in this campus, this needle shape, usually we made such kind of a very elongated shape for the needle of the campus. And one side, what you call north pole, the other side called the south pole. This looks very natural, but have you ever seen this kind of needles? This is south pole, this is north pole. We have a north pole and south pole at the sharp end in this cartoon, but here we have a south pole and north pole, broad side. Have you ever seen this kind of campus needle? This is very unusual. And why the North Pole and South Pole exist at this end point? Yeah, just imagine that if you're working on electrostatic problems, if we have a free charge in a metal surface, and if one end is very sharp, then the charge density at the very end of this structure is usually very high. This is the the working principle of the 치명으로 뭐죠? No, no, no. What I'm talking about the prevent the thunderline? Thunder? Yeah. I don't remember the English name. But to prevent we can see this kind of 피레침이 영어로 뭐죠? 생각이 나요, 갑자기. Okay, okay, okay. Yeah. So when the lightning is actually the breakdown of air between the cloud and the earth, and there's a very strong current is going from from the cloud to the earth. Then with this lightning load, we can prevent the damage of some buildings, right? And the working principle is here. The charge is very high density at the end of the metal system. And this reason is also same. They want to minimize the electrostatic energy. Instead of the field, the magnetic field, if we put the electric field, is same. So look at this. In this cartoon, or this one, this is the bar magnet, and all the metallic pin attached by the magnetic field, and they make such kind of attachment, not this kind of shape, because this is the lowest energy state. So in this kind of attachment, also they try to minimize the system energy. So if we have a ferromagnetic material with the strong external magnetic field, this ferromagnetic material is magnetized this direction, and we have a north pole and south pole here, and we have a certain straight field. This kind of field is what we call the straight field. And inside of the ferromagnetic layer, actually, north pole means we have a south pole here, and north pole, south pole, and so on. We have a south pole at the end. And because we don't have a monopole, we always play with the dipole. Dipole is the minimum structure of the magnet, as we already learned. And inside of this permanent magnet, we have a north pole here and south pole here. So there is some kind of internal field called the demagnetization field. Demagnetization means we want to suppress the magnetization. So this demagnetization field actually proportional to the magnetic moment, reverse direction, minus sign. So when we have a magnet, we always has a demagnetization field at the inside of the magnet, and the direction of the demagnetization field is always opposite to the magnetization direction. So we can say this kind of field induced by the magnetic moment. Okay. So yeah, this is also one more review for the electric energy for the spring, and the electrostatic energy of the capacitor is this one. And if you play with the inductor, we have this kind of energy, stored energy density, and we have energy density of this expression, and this is nothing else but this one. I think. Okay, so this is remind, and according to this magnetostatic energy, we have a external field and magnetic moment here. There's north pole and south pole here because we generate such kind of field. Okay, And the inside of this material, we said there is some internal field called the demarcation field. Okay. And this demarcation field solely depends on the surface pole distribution. If this distribution changes, this one is changed. So to minimize this kind of energy, this surface pole preferred certain position, and this totally depends on the shape. That's why we call this is the shape anisotropy. Okay. And this shape anisotropy, we can determine the H demand field is proportional to the minus M. And the left-hand side is vector, this is vector, and this proportional constant usually form of the tensor. So the more generally, the dimension tensor is more correct expression. Is second rank tensor, so they formed generally 3 by 3 matrix form. Okay.
Why is the ellipsoid shape?
Okay, I'm gonna say. Okay. If we assume the ellipsoidal shape, and if we apply the magnetic field parallel to the principal axis of the ellipsoid, we can diagonalize this dimension tensor in this simple form. Otherwise, always we have an off-time element. Yeah, this is very important. The ellipsoidal shape only generate this kind of diagonal shape, diagonalized dimensional tensor. Actually, it is exactly same for the electric field. If you apply the electric field for the dielectric material, there is some induced dipole moment, and they are also parallel to the principal axis. Only when the shape is the material form the ellipsoid. Otherwise, for example, simply say if we have some kind of a sphere and the magnetic field, there's some dipole here, the north pole, south pole at the end. But in this case, the H part will generate not uniform values. They generate non-uniform charge density to minimize the energy. But ellipsoid generate very well uniformly magnetized one, and the magnetic moment inside of this ellipsoid is exactly parallel to the field direction. For example, in a sphere, if we apply a field, the magnetic field at the end point, always they show such kind of bending. So in that case, the dimension tensor is not uniform. They should do positive benders. But fortunately, this kind of ellipsoid is mathematically very useful if you adjust the yeah. Actually, this ellipsoid equation for the ellipsoid, as you know,
So this one.
Okay. Usually the equation for the ellipsoid is simply x square a square plus b square y square plus g square over c square, so on. And depends on the relative size of A, B, C, this ellipsoid can be represented very long wire or flat or a sphere, and many things can be approximated. So once we obtain this dimension tensor component for the ellipsoid for given ABC, you can take some good approximation. And for example, by the way, there is very important mathematical conclusions. The all sum of this diagonal element nx, ny, and g must be 1 for the SI unit. But in a CGS unit, they give a 4, 5. This is the different definition. Mathematically, they are identical. Anyway, so according to this idea, we can easily obtain some very important geometrical case. For example, the films, which one is very important in many applications. So in that case, the film means we assume the infinitely large, large films. So then we just think about what's the physical meaning of the dimension field. Means if you have a moment in a film inside the films, and they generate the north pole at one end and the south pole at the other end. But we just said the film is infinitely long. Then the generated field from this plus minus sign, the north pole and the south pole, the field is very, very small. So we can ignore it. So that means this is 0, but we have a finite n. So the n must be 0. For the x direction and y direction is same because we are talking about the films. So as a result, the Dirac field for the g direction must be 1 or 4 pi. So that implies if we have a films and the mounting moment of the film, for example, is perpendicular. So we have a north pole and south pole here. Then there is some field inside of film in opposite direction, amount of minus ms. Okay. So this demarcation coefficient for the film is very important in many applications. So please, if you cannot understand, just to try to remember it. It's not difficult, just to remember this result. Here, I'm going to ask one question. How about the sphere? What can be the dimension factor for the sphere? Just imagine the nx, ny, and g for the sphere. Are they different? Can you distinguish x, y, and z? So they must be same. So when we sum up the same number, the 3 times, we got a 3n, and this must be 1. So you can obtain the Dirac field of the sphere is just 1/3. Actually, this result appeared in many electromagnetic problems because the depolarization factor is mathematically identical to the demagnetism factor, and the depolarization factor of the sphere is very important in many electrostatic problems. For example, if we have an electric field for the sphere, the dielectric sphere, then there's some induced polarization, and that is the very important in scattering problems. Okay, so please remember this one also. Okay, so the demagnetism coefficient is fully depends on the only shape, not the material's property like a magnetic moment or any kind of thing. Only depends on the shape. Okay. So that's what we call, this is the demagnetic energy or shape anisotropic energy, because of the shape, they prefer certain direction of the magnetization. So that is kind of the anisotropy. And also the physical origin of this energy is came from dipole interaction of the each poles. So sometimes we call this is dipole energy. But many people use several different names, and sometimes they said the demand energy, they determine the already demand energy, but they said another contribution of the dipole energy in other case. So sometimes it makes confusion. But please remember that the physical meaning of demand coefficient or the shear balance P are exactly same. Okay. And as I mentioned, in a thin films, this demand energy plays important role because they always generate the certain amount of the magnetic field, the minus G direction. If we have a plus G direction magnetic moment. So maybe some students in this room are familiar with the perpendicular magnetic anisotropy. But some of students maybe not familiar with this word. So I'm going to check out. Please raise your hand if you know about the PMA. What is the PMA? Jeong, you don't know what is the PMA? No? Please raise your hand if you know what is the PMA. Only my students don't see. Okay. The PMA is short word, the name of the perpendicular magnetic anisotropy, because in thin films, as I mentioned, they prefer the magnetization is inside of the film flame. That makes the lowest energy. But in many applications, we need the magnetic moment to the up direction or down direction. And only specially designed material has this chance. This kind of material, what we have, what you said, the perpendicular magnetic anisotropy material. So in short, we call this PMA. So this perpendicular magnetic anisotropy, to achieve the up or down direction of the magnetic moment, magnetization, they should be larger than the shape anisotropy energy. Yeah. The system always prefer the lowest energy. So to make certain condition, we need certain energy. So this is this part is the shape anisotropy energy in a films, because what we need is this is the demand energy, and we already learned this demand field is minus m for the films. So instead of this one, we multiply, we substitute m, so we got this term. So this is the energy density, not the total energy. This is the unit of the energy density, and this Ku is what you call the RS energy. It's also energy density, and they should satisfy this condition. Otherwise, the magnetic moment in the films they are lying in a plane. So this is very important condition. Okay. So let's back the expression for the energy density. So this summary, the electrostatic energy density is epsilon E square over 2, or if you write down the D field instead of the E field, we can write in this form. Or magnetic energy, we can write down this form or this form. And as you see here, these two equation, expression for this two equation is quite similar to elastic energy. This is the energy. This is energy density. That's the difference, big difference. But sometimes you saying this is just magnetic energy or electrostatic energy. But the correct meaning is this is energy density. So the unit is joule per meter cube. This is the unit of the joule. So that's sometimes they are big difference. But anyway, the mathematical expression is quite similar. Have multiply some constant with some square, right? So if your mathematical expression is similar, that means there is some common physics. Okay. So please remember this result. And what is the very important consequence of this dimension field? Okay, so let's think about this single domain structure. We have a North Pole and South Pole at the top and bottom of your samples, and we have a state field, right? And this kind of state field always generates certain amount of energy. And how you can reduce such kind of energy? There is some hint. If you make two domains here, we don't learn about what's the meaning of the domain, but domain means we have a certain range or certain area or certain volume where the magnetic moments are parallel. So if you have a up domain here and down domain here, this is up domain, this is down domain, then the total straight field from outside of a sample is always existing in this small area compared to the left-hand side. So in this case, the straight field generate magnetostatic energy is much, much smaller than the left-hand side. This side is a small energy. And what happens if you even smaller domain? The straight field is even smaller and they occupy only small area, small volume. So the magnetostatic energy of this multi-domain state is much small. So it implies they preferred this state instead of this single domain. That's why if we have some ferromagnetic material like for example, nail or pin made by iron, which one is known as a ferromagnetic material, but they do not behave like the permanent magnet because in normal state they form such kind of many domains, and the magnetic moment direction of each domain are random. Actually, not the random. They have some rules, but in a simple way, they form random, and the average value of this total magnetic moment are exactly zero. But don't confuse with the paramagnetism. When we talk about the paramagnetic moment, paramagnetic material, the direction of spin of each atom is random. But ferromagnetic material, they form the certain domain, and this size of domain depends on the material, but it's kind of order of micrometer or sometimes less than a few nanometer or something, but still is much larger than atomic scale. So in a ferromagnetic material means there is some spontaneous spin ordering at a certain distance. Then this distance is governed by many energies. And in this kind of multi-domain state, each size of domain is simply say order of micrometer something. That means they including thousands of millions of the spins. They are have the same direction. But if you think about the domain by domain, the direction is not the same. To align these spins for the multi-domain, we need external magnetic field. That's why we have such kind of hysteresis loop. Okay, so when we apply the external magnetic field, each domain, sometimes they rotate, sometimes they expand the area. The detailed dynamics of the spin motion is what we will learn. Okay, and so in a zero field, average value of magnetic moment is zero because it looks like random. But when we apply the magnetic field, the magnetic moment of ferromagnetic material feels the external field, and they try to align the field direction. So the total magnetic moment is increased, and with a certain amount of magnetic field, is all domain pointing the same direction. This is what we call the saturation. And when we reduce the magnetic field, they form the multi-domain, and this value is less than the saturation value. And for the negative field, they start to reverse some domain. And finally, a certain field we call the coercivity. Then the average value of mass moment is zero again. But we need a certain amount of negative field instead of the zero field. And if you apply the even stronger negative field, there we aligned against the negative field, and so on. So this is the kind of hysteresis rule. Okay. Mm. Mm. So let's get the PMA things. In a thin films, they always prefer the implementation. And when we make the magnetic moment is perpendicular direction, the energy difference, this in plane condition and the perpendicular condition is always this amount. 1 over 2 mu 0 ms square or 2 pi ms square. This is always positive. Okay. So please remember that all spins preferred in plane direction. To make this one, we need to give energy to the system larger than this one. They preferred this direction. Okay. How we can make such kind of energy? We're gonna some are we gonna talk about this kind of energy term? Okay, so this is a summary of the demand energy. Actually, to understand really the demand energy, you need to calculate this one. But usually that requires very, very complicated integrals. Maybe triple integral some things for the ellipsoidal geometry. And only few textbook handle this kind of difficult mathematical treatment. If you really want to calculate this dimension factor by yourself, maybe you can find some calculation for the depolarization factor instead of demagnetization. Depolarization is more widely used, so it's more easy to find the mathematical derivation. But the mathematics are exactly the same. Okay? Okay, so the next energy is what we call the magnetocrystalline anisotropic energy. Okay. So, by the way, what is the meaning of the anisotropic energy? That's the one of the important things. Anisotropic means opposite word to the isotropic. Isotropic means they don't care about the direction. Every direction are same, right? And what is anisotropic? Means they preferred certain direction and they hate certain direction. So means each direction has different, physically different. Isotropic system is much easier to handle because we don't need to care about the directions. So usually isotropic system has a spherical symmetry and only there is no theta or phi dependence. So mathematically much easier. But anisotropic system means they prefer a certain direction, so we need to describe the energy as a function of the direction. In a spherical coordinate system, the energy must depends on the angle theta or phi. Okay? And let's back to the crystal system. In a crystal system, they have the BCC, FCC, or ACCP, and there are many more crystals. Means there is some certain direction. You know, when we talk about the crystal, we always talk about the crystal direction, crystal axis, right? So that means this direction and the other direction is physically not the same. So in a crystal, always they have a certain anisotropy. But sometimes this kind of anoscopy will be cancelled out by the symmetry operation, so they will gonna suppress. But in a magnetic moment, okay, so experimentally, what you can observe is here ABC is for the ion, which one is BCC. When we apply the magnetic field, we measure the magnetic moment, and as you see here, each crystal direction shows different behavior. And as you see here, for the 100, they easily saturate with the small magnetic field. So let's say something here. But the other direction, for example, this 110, they required much larger field to saturate. Okay, so we can say, okay, the mass moment in ion, they preferred aligned to 100 direction. This is what we call easy axis because it's easy. And this direction is what we call the hard axis. Okay, it's very straightforward name. Why? Why they preferred certain direction? Because the spin they coupled with the orbital, right? Because this crystal direction there's certain orbital, and the other direction the orbital is different. So whenever there is some spin-orbit coupling, the crystal anoscopy must be exist. But some materials, this crystal anoscopy energy is very, very small, so we can easily ignore. But some materials is very, very strong, and we need to take account very carefully this crystalline anoscopy energy. So let me ask a simple question. If your sample is polycrystal, this crystal anoscopy energy will be important or not? Polycrystal means each spin direction of each grain is different, right? Even though they form the crystal structure inside of the very small grains, but if you're taking large scope, the orbital direction is crystal direction is almost random. So they will not cancel out each other. So in polycrystal films, actually when we grow the films by the sputtering, they usually form the polycrystal. So in that case, in plane direction, there is some chance of the crystal anisotropy, but usually they're gonna cancel out each other. But still, they have a chance to have a free-pod orientation in the films. For example, if you grow the FCC films, they usually make some one-on-one direction free-pod orientation. Then there is some chance of this direction of the critical energy. Anyway, so for the ion, as you mentioned, they preferred 100 direction, and for the FCC nickel, they preferred 111 direction, and for the cobalt, they preferred 0001 direction. But it is not a general rule, even though there is some other kind of BCC material, some BCC material preferred other directions. So it's material by materials. So you need do some experiment, or there's some theoretical result also. And the amount of the magnetic crystal energy is also different. For example, the cobalt, they required around 8 kilowatts of the field to saturate this direction. And it looks like not saturated. This is not large enough. But this guy is much smaller field. So means the crystal energy of the cobalt usually very high. Okay. And there is, do you have any question?
Oh, sorry.
No. Okay, there is one more comment. The energy difference of this crystalline NSP, the energy difference of the NSP is usually very, very small compared to the total system energy. in an experiment, even though it's a small variation, means if you align the magnetic moment of the ion to the 100 direction and 111 direction, they require certain field, means we need certain energy, and this is called the magnetocrystalline energy. This amount of energy is not that large compared to the total system energy. What I'm saying is, if you calculate the band structure of your energy, let's say this is gamma point and X point, and there is some band structure, something. And for the spin direction, for example, this one is for one direction, and the other band calculation shows something like this. This is this direction. This difference is not very significant, usually very, very small. As I said, the order magnitude of this band structure is order of electron volt, but this energy has only less than, usually they have a 10 to minus 5 electron volt something. So in a calculation, you need calculate the energy with the at least 6 significant digits. So that requires a lot of calculation cost. So that means the calculation is not easy. So many theorists try to calculate this energy, but it's very difficult, one of the very difficult calculation. Nowadays, the computing power is very powerful, so many people doing these things, but about 20 years ago, something is very challenging topics. Okay, so then how we can describe this kind of energy mathematically? As I said, this energy must be position dependence, the direction dependence, and this must be functionable theta or phi in a spherical coordinate system. So there is many kind of crystal analysis of energy, but in a simple case, we consider these two representative cases. The first one is what we call the uniaxial anisotropy. They usually appeared in the FCC and HSP structure. And the uniaxial means there is some axis, and this axis is the kind of unique axis. So energy depends how far from this axis. And this station and this station belong to the same axis, so they should have the same energy. So in other words, they have only 1/800 degree symmetry, or in other words, we have a twofold symmetry. And what is the most simple mathematical representation of this symmetry is simple cosine square or the sine square. So this kind of cosine square or sine square representation is not came from the very rigorous theoretical models. It's just empirical law. Most easiest mathematical representation is this one. But if you think about more complicated initial entropy, what you need is higher order term, like a fourth power of the cosine theta. But in many cases, we don't need such a high order. Sometimes it's very important, but we're going to focus on a simplest way. And these two energy expression is actually same physical meaning. If you have a positive Ku, which one is what we call the crystalline energy, actually, this is the energy density unit. And what's the physical meaning of this equation? What is the lowest energy in this energy expression? 김지수? When this energy term is minimized, what value of theta? So, 45? No, no, no. So now we are talking about the Ku is positive. So when cosine theta square is 1, they have a minus Ku. Okay? Then when cosine theta square is 1, exactly 0 or pi. So if we plot this energy as a function of theta, this term generate something like this. And here is, this is pi. Okay, this is 0. So this energy means the magnetic moment tripled, the angle of theta is 0 or pi. And how about this one? How about this one? No, they generate something like this. Just the shift of the constant energy. So this is what I'm saying, mathematically they're identical. But sometimes this one is more easy to use, sometimes more easy to use. Only mathematical reason. Physically they are same, so they generate the same result, but mathematically sometimes the difficulty is different. So sometimes I'm using this one, sometimes I'm using this one. For only the mathematical reason. Okay. And for the FCC and HSP, they usually have a unidirectional because, back to here, in an HSP structure, this direction is different, this direction. So it's natural they have this kind of, the C-axis is a kind of unique direction. And for the FCC case here, this diagonal direction is Z-axis, and that's usually the gross direction of the polycrystalline films. So usually they generate certain initial atmosphere. But for the BCC, here the BCC ion, they have a 100 axis. Then this direction and this direction, those all direction must be same. They're physically same. So this is what we call biaxial or cubic anisotropy. And they usually appear in a BCC structure. In the same reason, the mathematical description of such kind of symmetry, the most simple energy expression is this one. Here, alpha is the direction cosine for each axis. And in a three dimension, they form such kind of this is the simplest energy expression. You can have this kind of symmetry. But it looks very complicated, but when you think about the films, as we said, in a simple films, the magnetic moment is always belong to the XY plane, not the G plane. So the alpha 3 is 0. So this term is disappeared. Only remaining part, this alpha 1 square, alpha 2 square, and this is, we can rewrite by cosine theta square, sine theta square. Yeah, because the alpha 1 is cosine theta, then alpha 2 is sine theta in a direction cosine. So in this case, depends on the sign of K1, you can easily find which direction is EGHS. And they have a 90 degrees symmetry, so sometimes we call this is fourfold symmetry. Okay? So means 0, 90, 180, and 270 are physically same. So this direction, this direction, this direction, this direction are energetically same. Yeah. Okay, if you have a complex crystal system, not that simple FCH, PBCC, that's the simplest crystal structure. But if you have a more complex crystal system, this energy has more complex form. It's not, but it's not necessary to learn now. If you studied a very specified crystal system, you need such kind of energy expression for your crystal systems. But generally, it's much more complicated. So it's not necessarily learn in this situation. Okay. So if you draw the analysis energy surface, okay, this is the simple code for the Mathematica. Do you know Mathematica or Wolfram Alpha? This is the generate this kind of cartoons. Here, the direction from the origin to the surface is related to the energy. So, for example, A is corresponding sine, cosine, sine, cosine, and here this is the biaxial case. So, the energy of this system is lowest for the direction x, y, plus minus g, x, y, plus minus x, plus minus y. And for this one, is for example the anarchy energy is negative case. So in that case, they have a lowest energy along the one direction is the diagonal direction. And the final one is the cobalt case. The K energy is positive. Then the plus G direction or minus direction has the lowest energy. So reverse from the plus G to minus G, if you write this plot in a two-dimension, so there is some kind of energy barrier. This kind of energy barrier is we need to overcome this energy barrier to switch the magnetic moment. So that's why this magnetic energy is important, some magnetic applications. So I hope if you take a look this kind of three-dimensional structure, it's not easy to understand what is the physical meaning, but you need to understand this physical meaning with these equations to understand the energy things. Okay? 여러분들 이거 그림 이해하는데 좀 어려우면은 요 인터넷에서 if you can search this kind of things in Google, you may find more fancy surface models. So if you find them really good one, please let me know. I'm gonna update my lecture note. Okay. Okay. So I'm gonna skip this part. This is too much. Yep. So okay. Yeah. Okay.
캡슐하게 어느 스토피를 힘내고 강한 이제 이게 FC의
Okay. Her question is about the relation with the universal entropy and the PMA, some specific crystalline directions. Okay, so PMA has many sources, many kind of source, and now we are talking about only the crystalline energy. But many kind of PMA came from the surface energy. So surface energy is a little bit different from this crystalline one. But some crystalline energy, for example, the most famous example is the cobalt platinum or iron platinum L10 ordering. Here, L10 ordering means some kind of crystal structure. In that case, they preferred certain direction of the crystalline direction, and they usually, when we grow the cobalt platinum or iron platinum system, we adjust the preferred direction heading to the film normal. So that's what we can obtain the largest, very large PMM anisotropic energy for the certain materials. But some material or some case we can grow film. They have a very strong universal anisotropic energy in a certain direction of the crystal direction in in plane. So in that case, we can obtain the very strong in-plane universal anisotropic, not the PMA. So sometimes many students confuse the origin of each energy, but now let's focus on crystalline ion energy, but in a crystalline energy, there is some representative case of the uniaxial and biaxial. But there are many other sources, they form the uniaxial NSP or the biaxial NSP energy. For example, in a uniaxial NSP energy system, if you give a stress in certain direction, there is some other kind of NSP can be appeared. Okay. Okay, so this is the how it becoming the NSP energy, but maybe it's also too much for the student. Let's skip it. Okay. Here, I'm going to explain about the PMA. Oh, yeah, this is what I'm just saying. In a PMA, which one make the film magnetization is to the normal. There are many kind of source. We can categorize by two. One is the from the bulk. And other origins came from the interface. And as I said, the L10 ordering of the ion PT or ion palladium, this kind of special crystal structure, and also this kind of material, the crystal energy, having to the perpendicular direction, and also layers transition metal alloy, which one is very important in many applications. They say the origin is pair ordering between the layers and transition metal. And it's not that easy to understand, but maybe you can remember the just name. Okay. And also, we talk about the films. So the interface always plays very important role in thin films. So just to simply imagine if you have a ferromagnetic material here and there's non-magnetic material here, and at the interface, the spin, this direction and this direction are physically different. So they should have a different energy. But in some material, this state has a low energy, but some material, they have a they prefer the perpendiculation of the spin orientation. And that kind of material, we have a chance PMA called the surface PMA or interface PMA. Between the ferromagnetic layer and the non-magnetic materials. But sometimes, between the two ferromagnetic materials, for example, cobalt nickel, they also generate the PMA. So there is no general rules. It depends on the material by material. Okay. And just to simply say, the symmetry is breaking at the interface, then something happens. And there is some ferromagnetic layer, like a cobalt ion or cobalt ion boron and so on. And non-magnetic material can be palladium, platinum, even nickel, or some oxide will generate such kind of PMA. Okay. The reason I'm talking about this one is we're gonna talk about the PMA materials many times for the spintronics applications. So you may remember this, like how you can generate the PMA. And for the PMA material, for example, we have a cobalt or some other materials, but cobalt is one of the best one. And if we have a palladium or platinum, we have a such interface. And this is purely interface energy term. So you should remember that the dimension of energy. This is the energy density, dimension of the joule per meter cube. This is the total energy, and this is same physical same unit from the crystalline energy per volume. And this is what is this? This is the shear energy. This is also has a unit of the energy density, and this term K int, case of int means interface energy, and this is the interface energy. So we have a unit of the joule per meter square, right? So add up these three physical quantity, they should have same physical dimension, same unit. So what we need is we need to divide by the length, which one is corresponding ferromaterial thickness. And why we have a two? Because we have a two interface. So each one came from this single interface. So we have a two interface, we multiply two. So with this simple model, what you can do is, if you change the cobalt thickness in your films, in your sample, if you change the cobalt films, then you change the cobalt thickness. And if you, when you measure the experiment, you always measure this one. And if we multiply K, the thickness of cobalt in the left-hand side, we have this equation. And this is the experimental data, y-axis, this is x-axis, this is x, and this is y. And what is the physical meaning of these two number? This one is a slope of this curve. And this is the intersection with the y-axis. Okay? So by doing this kind of experiment, we can change the cobalt thickness and measure the K effective and plot it. We got a linear curve, the line. And in a line, you can obtain the two physical quantities, slope and the intersection. When you are doing such kind of experiment, linear fit, always you got a slope and the intersection. And usually they have an important physical meaning. That's why we are doing such kind of plot, the fittings. So from this experiment, we can obtain this DMAC contribution and the interface contribution. You can separate the measured value by these two physical terms. Which one is important to understand the ferromatic films? Okay, so this is what you call KTT plot. KTT plot, because we have a T here and K multiplied T left-hand side. So to understand the PMA for this film structure, always we need this one. Okay. Okay, this is the last slide. Now we are talking about the energy equation for the films, and the total energy of the thin film has this form. This is crystalline enthalpy, this is surface term, and this is the demand energy terms. And this first term depends on the cosine square, and the second term is actually this is another uniaxial energy contribution, but they preferred the in-plane direction. We have this energy equation. So we can mathematically convert it to more simple form, this form. And this term is a constant term, you don't need it. And you can rewrite the energy simply this new coefficient called effective anisotropy energy. And this effective anisotropy energy, we have a two positive term and one negative term. And once this positive term is larger than this one, this prefer the in-plane direction, this one is prefer the perpendicular direction. When they larger than the right-hand side, the mounting moment pointing up or pointing down, the perpendicular direction. But once they are smaller, the Dirac energy is larger, they aligned in plane. Here is very important point. There is no intermediate state. Once they are larger than the case one, they pointing up, even though they are just slightly larger than zero. Many students confused if they are comparable, they prefer the tilted direction. That is not true. For the simple single domain model, they preferred only one direction because even though this is small but non-zero, they will decide the direction. Okay, so please remember that point. Okay, so let me finish today's lecture, and next Wednesday we're going to talk about the domain and the domain structure. Okay. I have one question. How about the Wednesday lecture? Do you have any problems in Wednesday lecture? Because as you know, Thursday we have a big holiday. So is it okay, the Wednesday lecture? If some student has a problem for the Wednesday lecture, please let me know previously. And maybe you can participate the lecture by the Zoom, because I always open the Zoom class. Okay. Okay. So thank you.